Hello everybody, welcome back to our channel. In this episode we're going to be solving a Physics 7B electric circuits practice problem. As usual, if you're finding this content helpful, please make sure to leave a like and subscribe. It really helps our channel. So this is the circuit that we're going to be working with. We basically have 4 light bulbs in this problem, as well as 1 battery. And this is a 2-part problem, so let's just go ahead and read part A. So an uninsulated wire is connected from point 2 to point 4 on the diagram, and we basically need to explain how the brightness changes or stays the same when the wire is connected. So it could either be brighter, stay the same, dimmer, or off. So as you can see, I have this diagram over here. So this is the original diagram. I have all of my light bulbs, and because all of them are connected, so all of them are on, and all of them are a certain level of bright. So what's gonna happen for part A is that I need to connect a wire from 2 to 4, so like this. So this is the before diagram, and I kind of want to keep it because obviously what we're gonna be doing is comparing. So this is my after diagram, and basically what I'm doing is connecting from here to here, like this, right? Or it could be like outwards or whatever, but these 2 points are connected. Oh, and this is A, B, this is C, and this is D. So what's gonna happen once we connect this wire over here is that you're gonna have your total current just as before. So there is a total current, and then it's gonna split up. Some of it is gonna go down here, and then some of it is gonna go over here just as before. And then some of it was going this way, and then they reconnected. Except once the current gets over here, now you're basically given the current the option of either going through this wire straight to this corner or crossing through D, which is a resistor. So this is one of those cases in which, I've said this before on past videos. If the current has to choose between 2 paths of resistance, the current will prefer the path of least resistance, but it's still gonna split up. So it's gonna be a preference, and it's going to split up according to that preference, but you're still gonna have current going both ways. But the path of least resistance is different from the path of no resistance. So now that you have a path of no resistance, which is you can either go here or here, all of the current is gonna go through here, which means that D is basically going to be off. So light bulb D, is off. Final answer. So our new circuit, essentially, if we can redraw it, would basically look like this. So we have it basically looks like this, because D is not even turned on, all of the current is going. So an equivalent circuit would be to just have the 3 light bulbs that are still on. So now we have to figure out how this circuit compares to this circuit and how the currents compare, and then based on this comparison, we have to figure out if A, B, and C are brighter, the same, or dimmer. They are not off. I know as a fact that they are not off because all of them have electricity running through them, so off is not an option, but I still need to assess whether they are the same, brighter, or dimmer. Now, this quiz was sort of like special in the sense that we didn't ask for an equivalent resistance, we didn't ask for a voltage, we didn't ask for anything. So an option that students had was to argument their answers with like sentences and words and whatever. And then obviously depending on you know, how well argumented their answers were, or how right their answers were. Obviously that would you know, that would determine their score. But what I'm gonna do here, since, you know, I really have you know, what I feel is that I could like talk a lot, but that is honestly not as convincing as putting some actual numbers over here, or like actually trying to come up with equations in which I can just show you what is happening. So what I'm gonna do is I'm gonna use equations as much as possible, but just know that for this particular quiz we were a little bit lenient, and if you could explain something really well with words, then that was as good as an answer as just going through the equations. But I am definitely gonna use equations because, I mean, why not? We are in a physics class. So the first thing that I'm gonna do is compare the equivalent resistances for both of these circuits over here, because A is completely dependent on the total current of my circuit, and the total current is dependent on my equivalent resistance. So what I'm gonna do, since I have as much time as I want to, is I'm gonna reduce both of these circuits. Now I'm gonna skip a bunch of steps because this problem I decided to label as red. So if you've been following along with, like, you've done 10 other problems at least on this YouTube channel, so you know more or less what is going on. So I'm gonna take the liberty of not doing this step by step. But definitely feel free to do it step by step at home. You know, you're not under time pressure, so you get the luxury of just taking your time. And obviously this is great practice. All of the resistors, all of the light bulbs have the same resistors, so I'm just gonna call them R's. So let's see, these are two resistors that are in parallel, and they are also in series with this resistor. So let's see, so if I combine them, then this equivalent resistor is equal to R plus R squared divided by 2R. So this is 3/2 of R. Now over here I have this in series, in parallel with this, and then in series with this. So the equivalent resistor of this, again, feel free to do this step by step. I've been doing this for a decade now. So this is equal to R plus 2R squared plus 3R. So this is equal to 2/3 5/3 of R, like this. So this is the equivalent resistance of this circuit, and then this is the equivalent resistance of this circuit. So as we can see, did it go up or down? So let's see. So 5/3, 1.6, 3/2, 1.5. So the total resistance on our circuit actually went down, which means that because the total, if the battery stays the same and the equivalent resistance goes down, then that means that the total current before, I'm gonna call them before and after. If the equivalent resistance goes down, that means that your total current went up. So that means that this current, this total current, is actually smaller than this total current over here. So this guy actually increased, and this guy increased in comparison to this guy. Now, we know that power is equal to delta V times I, and is also equal to I squared divided by R. So the total current that is crossing A increased. So that means that this guy increased over here. And because this quantity increased, that means that the power increased, and because the brightness is related to the power, then this means that A is brighter. Final answer. So now we basically have to, okay, so that is 2 out of 4. So now we have to figure out what happens to C and what happens to B. So, before, it used to be the case that, so this branch has a total of 2R resistance, and this branch used to have 1R resistance. So let me just redraw it. So this is R, and so this is 2R if you combine these two, and this is just R. So whenever you had your total current over here, your total current would split. Obviously this is the path of more resistance, so it would split 1/3 going this way. Oh, this is 1/3 of the total current, and this is 2/3 of the total current, just because the current is always going to split up proportionately. So it would split 2/3 and then 1/3. But now on this circuit, it's basically going to split up 50-50. Oh, I have another one over here. Because this is R and this is R, then instead of splitting 2/3 and 1/3, it's actually going to split up 50-50, 1/2 and 1/2. So before, what I'm trying to say, I'm just trying to figure out how the current compares at C. So before, C got crossed by 1/3 of the total current. And after, C gets crossed by 1/2 of the total current, which is also a greater total current. So so this is basically so it used to be 33% of a lesser current, and now it's 50% of a current that is also a higher current. So obviously the current is increasing on C, and because it is increasing in C, if you use this equation, then you'll see that if the current is increasing, the power is increasing. So because C has more current, C is also brighter. So that is 3 out of 4, just by looking at the equations and just by looking at the circuits that we are comparing. Now we have to figure out what is going on with B. So B is definitely the reason why I decided that this problem is challenging, because you know, before we used to have 2/3 of a current, now we have 50% but of a greater current. So obviously you can't just use that logic to figure out B, because you don't really know how much it increased. So that is not something that we can just skip a procedure to do. We actually need to figure out a way to solve for the current at B. Well, not for the current, but just for the power dissipated by B. So what I think that we can do is maybe compare some loops. Yeah, so maybe let's just compare some loops. And what I'm gonna do is I'm gonna write some loop equations over here, and then see if that helps. So what I'm gonna do is I'm gonna loop like this, and then I'm gonna loop like this, and then see if I can compare those equations. And I think that if I do this, I'll be able to figure it out. So this loop, let's just call it the before loop, and let's just call this the after loop. So this loop starts at B, then crosses A, which is negative I total times R, and then it crosses B, which is negative, let's just call it the current that's crossing B times R, and this is equal to 0. Now the after would be basically the same, because I'm looping around like this, negative I total R minus IB R is equal to 0. Now if I compare them both, I basically want to know if this term went up or down going from before to after. So and obviously this is the total before scenario and this is the total after, so they are different. So I just basically need to figure out what's going on with these ones. Now E is the same, like we have the exact same battery for both of them, so this is not gonna be a difference. And R is also the same, like the light bulbs themselves haven't changed. So the only thing that is different is that this guy from before to after, we know that there was an increase. So this guy going from before to after, this guy went up. And if everything needs to, stay equal to 0, because the loop rule still needs to apply even if I short out a resistor, then this means that this guy actually went down. Just to keep the just to keep energy being conserved on a loop. That means that because the total current increased, this current actually decreased. So now I can finish my problem, because IB decreased going from here to here. Then if I use my power equation, if my current decreases, then that means that my power decreases. So, PV decreases and B is dimmer. 1 M or 2 M's, I don't know, I don't care. So this is how I know, as a matter of fact, that B actually has to be dimmer. So this is my final answer for part A. A little bit of a tricky situation because I had to compare circuits. But it is done. Off, brighter, brighter, dimmer. So let's just go ahead and do part B. So I do have a new piece of paper for part B. This is the initial circuit, except now we're gonna do something different to it. So let me just go ahead and read the instructions. Let's see. So the instructions say, in the original circuit, without the wire from 2 to 4, so the original circuit, bulb D burns out. That is, the wire inside of it breaks. Explain how the brightness changes compared to the original circuit. Okay, so basically what happens, again, this is the before and this is the after. So after it breaks, my circuit is basically gonna look something like this. because once this thing breaks, the wire breaks, you know, as instructions say. So there is a difference between this circuit and this circuit. This is a short circuit and this is an open circuit. So this light bulb is shorted out, this light bulb is burnt out. So this is a difference, and obviously this is gonna change everything, because now my equivalent circuit is gonna look different. First of all, final answer for D is that D is off because it doesn't even work. So that's easy. Now on this circuit, I have to notice that once the current gets here, because this is an open circuit, it can't actually flow through here. So because it can't actually flow through here, this resistor is also off. So C is actually also off. Remember, electricity needs to be flowing, and in order for electricity to be flowing, we need it to be able to loop around something. So this breaking off basically breaks this off. And this is actually, you know, on old school, or, you know, some of the, this reminds me of Christmas lights, right? So you know how old school Christmas lights, if you have like a bunch of them together and like literally one of them breaks, every single Christmas light was gonna break. So you had to like literally go and try to find which one was broken. Well, this is basically what happens, right? So you have a light bulb, and since it burns out, it basically, you know, now electricity is not able to flow through the entire branch. So even though technically it was just one little Christmas light that burned out, the entire circuit or the entire branch didn't work. Because light bulbs, Christmas light bulbs also had branches, right? So you have like an entire branch that doesn't work, but then you would also have like other segments that would work. Well, this is what happens, like you just burnt out a branch. But anyways, so my new circuit is basically, you know, my new functioning circuit is this, with just A and B, because C is off and D is off, so we don't even bother about them. So now I need to compare this circuit with this circuit over here. Now my before circuit, so I already know that my equivalent resistance, so I'm not gonna do this again, but my equivalent resistance is just the same as over here, so it's 5/3 R. Now for this circuit, my equivalent resistance is equal to just 2R, like this, because these are just two resistors in series. Now this means that my equivalent resistance actually increased like this. So now, because my equivalent resistance increased, what's gonna happen if I loop around, you're gonna see that my total current actually decreased. If you increase your total resistance, then your total current decreases. Now, the total current is the current passing through A. So just by using my equation, so for A, the total current actually went down, so it decreased. So for A, because this total current went down, then that means that A is dimmer. Because now instead of having an increase in total current, now we have a decrease in total current. So now instead of being brighter, A is actually going to be dimmer. So now we have to figure out part B. So part B, I'm sorry, light bulb B. So for light bulb B, I'm gonna use the same procedure that I did in order to figure out B before. So I'm just gonna loop around 2 times And this is definitely going to be the fastest way to figure this out. So my loop before is battery minus I total times R minus the current crossing through B times R is equal to 0. And then after, we basically have the same thing. Oh, but now this is actually the total current. So this is also I total R, and this is equal to 0, like this. Now, obviously, this is total before, and these two are after, like this. Which I think that you can clearly see where this is going. So, but let's just go ahead and do this. So E is going to be exactly the same for both of this. So E doesn't matter. These R's doesn't really, again, are gonna stay the same. So now we basically need to compare how this term compares to this term over here, because I know that before and after, so this term over here, because the current went from high to low, this term, the entire term went down like this, right? Just because this is the same R, and I know that our total current was high and then it went down. But now I have to compare IB with the IB before with the total now. And I know that in order for this to stay in equilibrium, then this new current crossing through B, this multiplication has to be greater than this multiplication so that everything can be equal to 0, which means that the current crossing B is now greater than before. And because of that, because the current for B went up, then that means that the power that B is dissipating went up, therefore B is brighter. Final answer, just by comparing the currents. Another way in which you can look at this that maybe is a little bit more straightforward is if we remember that P is also delta V squared divided by R or multiplied by R? Multiplied by R, like this. Wait. So P is VI and V is IR. No, multiply by R. Yeah, this is correct. So this is delta V before, and this is delta V after. So if you're thinking that maybe it's a little, weird comparing a current through B through the total current after, just compare delta V. So this entire term had to go up. And because P is also delta V squared times R, if this term goes up, then this has to be brighter. So that's another way to look at it. But yeah, regardless of how you look at it, B has to be brighter, A has to be dimmer, and these two guys aren't even turned on at this point. So this is the end of this problem. Again, this was a little bit of a tricky quiz in the sense that you could either use equations or just come up with a very good argument that you could just talk about. Obviously, if I'm gonna try to put up a tutorial in YouTube, I would rather use equations because I think that it is easier to convince someone with equations. So I really hope that this was useful, but again, if you could come up with very good arguments that were equivalent to the equations, then that was good as well. So I hope that this video was useful to you guys. Please make sure to leave a like if it was. If you have any questions, leave them in the comments. We do read the comments, and I will see you guys on the next video. Okay, I just have a little note on how I solved the problem, because I just noticed something and I definitely realized this at the end of the video, but I just wanted to check it out. Whenever I was working through this problem, first of all of the logic and all of the solutions are okay, but whenever I was solving this problem, I was working with you know, an incorrect version of this equation. We are given 3 equations for the power dissipated by a resistor, and you know, whenever I solve these problems, I honestly just use, you know, I just remember all of the equations. But it seemed that I remembered an incorrect equation because I used I squared divided by R instead of I squared multiplied by R. And then in the end, I also used B squared multiplied by R instead of B squared divided by R, which essentially means that I flipped these R's. I just wanted to point that out because obviously I made a little bit of a mistake, so it needs to be pointed out. However, I'm not gonna redo the video because my logic is still sound, which basically is that whenever I was using these equations, luckily for me, I honestly wasn't even looking at the R's. I was just looking at the current going up or down. So even if I had used, you know, even if I had used I squared R, then I would still be looking at whether the current increased or decreased, and then that is directly proportional to P, regardless of where the R is. And again, over here, this should have been divided instead of multiplied. And whenever I use this one, I wasn't really looking at R. What I was looking at was delta V. So because delta V increased, the power increased regardless of where the R was. So I'm not gonna do this problem again because my logic and my final answer is still the same. Like my final answers are still right. They are all the same and they are still right. So R didn't even come into play on this part, but I thought that it was very important for me to just add up this, you know, just sort of that I realized when I finished the problem that, you know, because I just do this by memory, that I flip these R's. But again, it really doesn't affect this problem, and whenever you're working with a quiz, of course, you don't have to memorize the equations. We always put them on the footnote of the quiz, which is something that I had to look closer to once I finished the video, and then I was like, oh shoot, I just missed this. But again, so just make a note on your notes that you know, this should have been multiplied and this should have been divided. And if you basically start over the problem, you'll see that you're gonna get literally the exact same answers, because what you're looking at is I and V, and the R, it really doesn't matter if it's multiplying or dividing in this case, and luckily for me. So anyways, so that's a little bit of a note that I wanted to add because I just realized that this happened. So thank you, and I'll see you on the next video.